The universe's first breath, a journey from nothing to everything. When we close our eyes and sink into the silence of our minds, the universe's most fundamental question emerges. How could everything, all of this existence, have been born from nothing? Take a moment to consider the reality we inhabit right now. Every star piercing the darkness of night, every galaxy dancing in the Milky Way's spiral arms, every atom composing our bodies. How did this staggering complexity, this vast cosmos stretching billions of light years in every direction, arise from absolute nothingness? We're not talking about empty space here. We're talking about something far more profound than a void containing not a single particle or energy wave. We're talking about absolute nothingness, where matter, energy, and even time itself didn't exist. Yet here we are. This is the deepest mystery that's captivated minds throughout human history, standing at the crossroads of physics and philosophy. How can something emerge from nothingness itself? If you enjoy these kinds of deep, contemplative questions that shift how you see reality, consider subscribing to our channel and hitting that like button if you haven't already. Your support helps these explorations reach more curious minds, pushing the boundaries of existence. Now, prepare yourself. Our journey toward that fundamental question begins. To dive into the heart of this question, we need to establish what we mean by nothingness. In everyday language, when we say nothing, we usually imagine an empty room or the dark distances between stars. But that's not nothingness in the scientific sense. Even the darkest void of space we observe is actually full of activity. It's a place where quantum fields constantly fluctuate, where virtual particles exist for an instant before vanishing, where energy trembles in whispers. At its most fundamental level, the universe's fabric is never truly still. But the question we're pursuing points to a state where even this quantum foam didn't exist. Imagine a void so complete that there's not even a canvas to paint on, no stage where the laws of physics apply, no river where time flows, no space where events can occur. This is a state of absolute nothing. Not even potential exists. Here lies the greatest paradox about the universe's beginning. The question of how existence sprouted from this absolute nothingness challenges everything we intuitively understand. On one hand, we have everything, trillions of galaxies, countless stars, and on at least one planet, conscious life capable of questioning its own existence. On the other hand, we have the absolute nothingness from which this everything supposedly arose. Bridging this chasm has become modern cosmology's greatest ambition. For decades, scientists have tried to piece together this puzzle. Was our universe born from a quantum fluctuation in an unstable void? Or did a cosmos before ours collapse in on itself and explode again, starting a new cycle of existence? Could the universe have always existed in some form? If you're thinking the Big Bang is the ultimate answer on this journey, you might be mistaken. The Big Bang is our strongest theory, marking the beginning of the universe as we know it, the moment when time and space began expanding. But this theory doesn't explain what triggered the explosion, or what existed before that moment. The Big Bang isn't an answer, it's a doorway to deeper questions. Reality might be stranger, more incomprehensible than we can imagine. Perhaps the very word beginning is an inadequate concept for understanding the universe's true nature. To solve this mystery, we first need to understand how our ideas about nothingness have evolved throughout history. Let's witness this concept's journey from ancient Greece to the modern world of quantum physics together. Because we can never fully grasp how everything began without understanding what nothing means. The evolution of emptiness from ancient philosophy to quantum foam. On this profound journey to understand how everything arose from nothing, we must first descend into the foundations of the idea of nothingness rooted in our minds, into the depths of intellectual history. Modern science's view of the void is actually the result of centuries of philosophical and scientific dialogue. Thousands of years before us, in ancient Greek lands, thinkers like Aristotle firmly rejected the idea that absolute emptiness could exist. According to him, nature abhorred a vacuum. This simple but powerful statement would dominate Western thought for nearly 2,000 years. For Aristotle, the universe was a completely filled structure that didn't allow for gaps. To him, space always had to be filled with something, sometimes air, sometimes fire, sometimes an invisible substance he called ether. This thinking stemmed from the belief that the universe wasn't a meaningless void, but an interconnected whole where every part served a purpose. For something to exist, it needed to exist within something else. Therefore, the idea of absolute nothingness seemed illogical and even impossible to them. This idea remained at the center of scientific thought for so long that questioning it was nearly impossible. But in the 17th century, a scientific revolution occurred that would fundamentally change how we view the universe. Galileo's observations, and later Isaac Newton's work, stripped the universe of philosophical interpretations and transformed it into a mechanism governed by mathematical laws. Newton defined space with completely different eyes. To him, space was an absolute void where objects moved according to predictable laws, a passive backdrop containing everything but interfering with nothing. Aristotle's living, filled universe was replaced by Newton's cold, mechanical, and most importantly, empty universe. Space no longer had its own structure or character. It was simply the vast, silent stage where the universe's play was performed. This idea was in perfect harmony with Newton's laws of motion and gravity, and it quickly gained acceptance in the scientific world. The idea that the universe was a great void became part of the new rational worldview brought by the Enlightenment. But even Newton's absolute void concept didn't dispel all doubts, particularly in the 19th century when scientists tried to understand light's nature. They faced an old problem again. Just as sound needs air to propagate, light waves were thought to need a medium through which to travel. If space was completely empty, how did sunlight reach Earth? To solve this problem, scientists proposed a hypothetical substance they called the luminiferous ether, invisible, weightless, and filling all of space to carry light. The ether refilled Newton's void, but did so without disrupting the universe's mechanical operation. This theory allowed physicists to explain light's behavior for a century and revived the belief that space wasn't actually empty. But toward the end of the 19th century, a famous experiment would change everything. The Michelson-Morley experiment was designed to detect Earth's movement through this hypothetical ether. The logic was simple. If Earth was moving through ether, light's speed should vary, even slightly, depending on the direction of motion. The experiment was repeated many times with incredible precision, but the result was always the same. There was no change in light's speed, not the slightest trace of ether to be found. This was a major blow to the physics world. The invisible medium on which theories had been built for years, it turned out, had never existed. This shocking result set aside both Newton's absolute void concept and the ether theory attempting to fill it, bringing science to a new crossroads. If space was neither filled as Aristotle said, nor a passive void as Newton imagined, nor a medium covered with ether, then what was it really? This question that classical physics couldn't answer would, at the beginning of the 20th century, open the door to Einstein's revolutionary theories and the strange world of quantum mechanics. Our understanding of the void's nature was about to change once again, and this time much more radically. The quantum revolution, when nothing became something. With the collapse of ether theory, the physics world found itself in uncertainty. If space was neither completely full nor completely empty, what was it? The answer to this question began to emerge at the beginning of the 20th century, with two great revolutions that would fundamentally change humanity's view of the universe. The first of these revolutions was Albert Einstein's theory of relativity. Einstein removed space from being a passive background and transformed it into a dynamic structure that could stretch, bend, and be shaped by mass, united with time. Gravity was no longer a mysterious force pulling objects toward each other. It was a consequence of massive objects bending this space-time fabric. The sun bends the space around it like a bowling ball, bending a stretched sheet, and Earth moves along this curved path. This was a radical break from Newton's absolute void concept. Space now had a character, a structure. But even Einstein's dynamic universe hadn't yet fully illuminated the void's deepest secrets. The most shocking and strange change would occur with the rise of physics' other great revolution, quantum mechanics. Quantum mechanics showed us how strange and counterintuitive reality is at the smallest scales. According to this new understanding, absolute emptiness, absolute nothingness, was actually impossible. Even in the most perfect vacuum, in a field from which all matter and radiation had been removed, energy whispers never stopped. This field was now called the quantum vacuum. This vacuum was like a sea of energy constantly frothing at the boundaries of existence. Within this sea, energy packets, called virtual particles, were born from nothingness for an instant, then returned to nothingness in the blink of an eye. These particles existed for such a short time that directly observing them was impossible. But their existence wasn't theoretical fantasy. Their indirect effects could be measured, and these effects proved that the void wasn't empty at all. One of the most concrete pieces of evidence for this incredible idea is the Casimir effect, proposed in 1948 and later confirmed by experiments. According to this effect, two metal plates placed very close together are pushed toward each other by the void between them. The reason for this pushing force is that the quantum vacuum outside the plates contains more virtual particles and fluctuations than the narrow space between the plates. This external energy pressure becomes a tangible, measurable force bringing the plates together. This experiment showed beyond doubt that the quantum vacuum wasn't just a mathematical concept, it had real physical properties and could create an effect on matter. The void was no longer the absence of matter, but an active participant in the universe. Quantum field theory took this idea even further. According to this theory, every type of fundamental particle in the universe, electrons, quarks, and others, has a field spread throughout every point in space. Even when no particles exist, these fields continue to exist and constantly fluctuate. For example, the Higgs field filling all of space is what gives fundamental particles their mass. If this field didn't exist, the fundamental particles making up matter couldn't exist in the form we know. So the most fundamental property of the matter composing us and everything around us depends on an invisible field filling empty space. This new understanding of nothingness changed cosmology forever. The mysterious dark energy causing the universe's expansion to accelerate is thought to be closely connected to this intrinsic energy of the quantum vacuum. Some scientists believe this cosmic pushing force originates from the void's own energy. However, the massive gap between theoretical calculations and observed values remains one of modern physics' greatest mysteries. This journey into the void's nature represents one of the greatest intellectual leaps in the history of science. Nothingness, once a philosophical abstraction, then transformed into a passive stage and finally understood as a dynamic structure frothing with energy, now lies at the center of our theories about the universe's beginning. The idea that this active void might have ignited that first spark giving birth to the entire universe will be our next stop. From quantum whisper to cosmic roar, the birth of everything. We've now left behind the old passive meaning of nothingness in our minds. We've begun to see it not as classical physics' silent void, but as quantum mechanics' constantly moving, potential-filled sea of energy. This new perspective brings us to one of the most fundamental questions about the universe's beginning. If even the void is this active and full of energy, could that first movement that started everything have come from the void itself? In classical physics, a vacuum is simply the absence of matter. But when we descend into quantum physics depths, this picture completely changes. There, absolute stillness doesn't exist. Even the emptiest piece of space we can imagine is full of energy fluctuations, virtual particles dancing on that fine line between existence and non-existence. These particles are a natural trembling of the universe's fundamental fabric. They appear for an instant and immediately disappear again, mixing back into the energy sea. They are reality's background whispers that never end. So could that massive event that started everything we know, the Big Bang, have been triggered by one of these whispers? This is one of modern cosmology's most shocking and elegant ideas. According to this theory, our universe might have begun not with a massive explosion, but with a single quantum fluctuation arising from an unstable void state. We can compare these fluctuations to small bubbles suddenly appearing and disappearing on the surface of boiling water. Normally, almost all of these bubbles extinguish as quickly as they form and return to the water. They're momentary, transient events. But according to this theory, under incredibly rare conditions, one of these bubbles might become stable instead of extinguishing and suddenly begin to expand. The universe's beginning might have been just such a moment, the moment when just one of countless virtual particle fluctuations won the cosmic lottery, escaped annihilation, and began charting its own destiny. This idea doesn't eliminate the Big Bang. On the contrary, it provides it with an origin story. The Big Bang perfectly explains how the universe expanded and cooled from an extremely hot and dense state, but it doesn't say how that first hot and dense state came to be. The quantum fluctuation theory fills this gap. According to it, that first state could be a seed born from the void's own energy. Normally momentary, this energy fluctuation became stable for an unknown reason and accumulated tremendous potential energy within itself. This energy is the source of all the matter and energy that would form the universe we know. This means the universe didn't need an external cause to exist. The beginning could have already been written into the void's own nature as an inevitable probability of quantum laws. Even imagining this thought in our minds is difficult. Imagine a pre-universe state where time and space don't yet exist as we know them. A quantum vacuum consisting only of pure potential, and within this infinite sea of potential, at a random point, a tiny energy fluctuation follows a different path from the others. Instead of ceasing to exist, it chooses to exist. This choice instantly leads to the birth of space itself, time itself, and their evolution at an incredible speed. Every galaxy we see, every object we touch, every thought we think is an echo billions of years later of that first momentary, random event. This reminds us how fragile our existence might be and how extraordinary a coincidence it could be the product of. If a quantum event could start our universe, does this mean other universes might be being born right now in other corners of reality? This possibility leads us to the next step, inflation theory, which explains how that tiny spark transformed into this massive cosmos we observe. Because that first fluctuation was just a beginning, the real story lies in that moment's evolution into infinity in less than a trillionth of a second. Cosmic inflation, the universe's exponential growth spurt. The idea that our universe could have been born from a momentary quantum fluctuation, practically from nothing, stretches our mind's limit. But this is only the beginning of the story. How did this microscopic seed transform into the cosmos of mind-boggling size we observe today? How could a point smaller than an atom expand enough to contain trillions of galaxies? The answer to this question lies hidden in one of modern cosmology's most powerful and surprising theories: cosmic inflation. According to this theory, the universe expanded at a speed beyond our imagination in the first moments of its existence. This wasn't an explosion of the kind we know. It was more like a silent, uncontrolled but incredibly powerful expansion. It was space-time fabric itself reaching mind-boggling dimensions in less than a trillionth of a second. This extraordinary theory not only explains how the universe grew so large, but also offers elegant solutions to some of the cosmos we observe's most fundamental features. For example, wherever we look in the universe, we see that on large scales it's surprisingly uniform, homogeneous. Two galaxy clusters billions of light-years apart from each other, who never had enough time to communicate with each other since the Big Bang, have almost the same temperature and properties. How can this be? Inflation theory says those distant regions were actually very close once, just before the universe began this sudden expansion. They were so close they had plenty of time to reach thermal equilibrium. Then inflation suddenly flung them to opposite ends of the universe. The uniformity we see is an echo of their shared past. Another great mystery inflation solves is the universe's geometry. Our observations show that on large scales, space is almost perfectly flat. This means it behaves like a flat piece of paper rather than a curved surface. However, for the universe to achieve such perfect flatness after the Big Bang requires an almost impossibly precise initial condition. This situation is like trying to launch a pen so it balances on its tip. Not impossible, but incredibly difficult. Inflation solves this problem with a simple idea too. Imagine a small wrinkled balloon. If you inflate it to massive proportions, you'll notice that any small part of its surface appears completely flat to you. Inflation did exactly this to the universe. It expanded it to such an immense size that the part we can observe remained a smooth patch on the surface of this massive cosmic balloon. So what triggered this mind-boggling expansion? Scientists think this process was governed by a hypothetical energy field they call the inflaton field. In those first moments of existence, this field, more dominant than all other forces in the universe, created a kind of anti-gravity effect. While gravity normally pulls matter together, the inflaton field pushed space itself, forcing it apart with incredible force. This incredible pushing force expanded the universe exponentially in the smallest fraction of a second. Then this process suddenly ended. The inflaton field decayed, releasing its tremendous accumulated energy. This energy created that dense soup of particles and radiation filling the universe, what we know as the Big Bang's hot beginning. So, according to this model, inflation isn't the Big Bang itself, but the event that came just before it and triggered it. Perhaps inflation's deepest legacy is planting the seeds of all structures in the universe. That first quantum fluctuation didn't have perfect smoothness. Within it were tiny random energy differences arising from quantum uncertainty. As inflation expanded space itself, it also stretched these microscopic quantum fluctuations to massive dimensions. These tiny density differences that were once at subatomic scales suddenly spread across intergalactic distances. Billions of years later, gravity would gather matter in these slightly denser regions and initiate the formation of the stars, galaxies, and galaxy clusters we see today. So every point of light we see in the night sky, every galaxy, owes its existence to a quantum tremor in that first moment. Inflation was the conductor that transformed the quantum world's whispers into a cosmic symphony. Cosmic inflation theory, while explaining how our universe reached its current massive dimensions from that first microscopic moment, opens the door in our minds to a much deeper and dizzying possibility. What if inflation, that mind-boggling expansion process, didn't stop everywhere at the same time? What if the slowing that created our universe and triggered what we call the Big Bang is just one calm island in an infinite ocean? This question leads us to a concept called eternal inflation that could change our entire perception of existence. According to this theory, space itself as a whole never stopped expanding. It continues to eternally inflate, creating new space-time fabrics. The universe we can observe is just one of trillions of pocket universes, bubble universes in this infinite expansion ocean where inflation momentarily slowed and energy transformed into matter. To visualize this idea in our minds, imagine a large pot of constantly boiling water. The water itself is that main space, eternally expanding. New steam bubbles constantly form on the surface. Each of these bubbles is a bubble where a new universe is born. Our universe is just one of these bubbles, and this process never ends. While our universe formed billions of years ago, perhaps right now, in another corner of that eternal ocean, a brand new universe is being born. According to this theory, the Big Bang isn't a unique and singular event. On the contrary, it's an ordinary birth moment repeatedly occurring in this constantly frothing cosmic fabric. Our universe is part of an infinite cycle of birth and becoming. This situation brings with it a much more surprising question about the nature of existence. Do these other bubble universes resemble ours? The answer is probably no, because each bubble universe is born from its own quantum fluctuation, a random energy exchange. This means each one's initial conditions and perhaps even physical laws could be completely different. In some universes, gravity might be much stronger than ours, and these universes could collapse in on themselves the moment they're born. In others, different fundamental forces that don't allow atoms to come together might reign, making them starless, galaxyless, completely sterile and lifeless voids. Some might have an unimaginable number of dimensions or completely different particles. The natural existence could have infinite different versions that stretch our mind's limits. String theory places this possibility on even more concrete ground. According to this theory, those tiny vibrating strings that are reality's most fundamental building blocks can be arranged in a mind-boggling number of different ways. Each arrangement corresponds to a potential universe with different physical properties. This is called the string theory landscape, a vast cosmic palette of possibilities containing an almost infinite number of options. Our universe is just one of those in this infinite landscape of possibilities that has that special and rare combination of physical laws allowing the formation of stars, galaxies, and ultimately life. This might also explain why our existence appears so precisely tuned. It's not design, it could simply be statistical necessity. In a place where there are countless attempts, it's inevitable that at least one provides the right conditions for life. This idea changes our entire perception of our place in the universe. We now find ourselves not at the center of existence, but on one of countless islands on the vast cosmic constellation we call the multiverse. Everything we see, billions of galaxies and trillions of stars, might actually be just a tiny fragment of a much larger puzzle. On one hand, this is a humbling thought that levels humanity's cosmic pride, but on the other hand, it's an extremely liberating idea, showing how rich, how diverse, and how awe-inspiring existence can be. Our journey is now evolving from understanding a single universe's beginning toward grasping a reality of countless beginnings and infinite possibilities. The cyclic universe. What if there was no beginning? The idea that our universe could be one of countless bubbles in an infinite expansion ocean deeply shakes our view of the concept of beginning. But what if we need to completely abandon the idea of a single beginning? What if the Big Bang wasn't that first moment, as the name suggests, but more like a moment of rebirth? These questions open the door to one of modern cosmology's most poetic and radical alternatives, the cyclic universe model. This thought whispers that our universe isn't the first word written on a blank page, but perhaps just the latest sentence in a much older, possibly infinite story. This is a cycle of existence with no beginning or end, eternally repeating itself. This idea isn't actually unique to modern science. Its roots extend back to humanity's most ancient philosophies and belief systems. Many ancient cultures, like Hindu and Buddhist traditions, imagined the universe in a constant cycle of creation and destruction. According to them, the cosmos is born, lives, dies, and then is reborn from its own ashes in an infinite rhythm, like the seasons. This means the universe has no beginning or ultimate end. It only exists in infinite transformation. In the 20th century, science began to rediscover this ancient intuition in its own language, mathematics and physics. Modern cyclic universe theories attempt to take this philosophical foundation and place it in a scientific framework. One of the best-known versions of these modern theories emerges from the Big Crunch scenario, once thought to be the universe's ultimate fate. According to this idea, the pushing force driving the universe's expansion will one day weaken and gravity will prevail. Then everything will reverse. Galaxies will stop rushing away and begin pulling back. Space-time fabric will contract instead of expanding, and after a countdown lasting billions of years, the universe will return to that incredibly hot and dense state where it began. According to classical physics, the end of this collapse is a singularity, a dead end where all matter and energy are crushed into a single point of infinite density, where the laws of physics become meaningless. But the story doesn't have to end here. This is where quantum mechanics enters the stage and shines a light of hope on classical physics's dark ending. At the smallest scales, reality's rules change. While gravity tries to crush everything into a single point, that fundamental uncertainty in quantum mechanics' nature creates a kind of counter-pressure, like an invisible hand preventing the universe from completely annihilating. This hand stops the collapse not at a singularity, but at a compression moment with mind-boggling but finite density. And after that moment, the accumulated tremendous energy pushes the universe back outward. The collapse becomes a bounce. This is the heart of the Big Bounce theory. According to this model, the Big Bang was actually the result of a previous universe's collapse and subsequent rebound. This means the universe could have a history, a past that came before us. We might be just the current link in an infinite chain of universes. Even more fascinating is the idea that each new universe could carry traces from the previous one. Just as a tree's rings give information about past years' climate, echoes of the previous cosmos might be hidden in our universe's most fundamental features. Perhaps those faint temperature fluctuations in the cosmic microwave background are not just birth pangs of our universe, but also ghost traces of a previous universe's death moment. This theory makes the question, when did it begin, meaningless, because there is no beginning, only infinite now, infinite transformation. Existence isn't a one-act play, it's an eternal theater, constantly restarting, perhaps staged with slight variations each time. The brain collision, birth from hidden dimensions. The idea that the universe could be an infinite cycle of rebirth takes the concept of beginning beyond time. But what if the mystery of the beginning is hidden not in time, but in other dimensions we can't see, whose existence we're not even aware of? This question leads us to one of modern physics' most complex and fascinating areas, an alternative creation story offered by string theory. This story depicts our universe's birth not as an explosion from a single point, but as a massive event occurring within a much larger reality, a collision. This is a theory that takes the Big Bang's cause from the beginning of time and places it in the depths of dimensions. To understand this idea's foundation, we first need to grasp string theory's view of reality. According to this theory, the universe's most fundamental building blocks aren't point-like particles as we know them. Instead, everything consists of incredibly tiny one-dimensional energy threads, strings, constantly vibrating like a violin string. These strings vibrating in different ways creates different fundamental particles, electrons, quarks, photons. Just as a violin string produces different notes, these cosmic strings' vibrations create the universe's music, matter, and forces. This elegant idea has the potential to unify all of nature's fundamental forces under one roof. But for this unification to be mathematically possible, the theory has a surprising requirement. The universe must have far more than the 3 spatial and 1 temporal dimensions we perceive. String theory predicts the universe could have 10 or 11 dimensions. So if these extra dimensions exist, why can't we see them? According to the theory, these dimensions are either curled up on themselves at scales smaller than an atom, or we, as beings trapped in our 3-dimensional world, can't perceive them. This is where the idea known as brain cosmology comes into play. According to this model, our known 3-dimensional universe is nothing more than a massive membrane, a brain, floating in this much larger multi-dimensional space. We're like pictures drawn on the surface of this massive brain. All our galaxies, stars, and existence reside on this brain, and we cannot exit it. But we're not alone in this multi-dimensional space. Other brains like ours might be floating on parallel planes. Each is a potential other universe. According to this model, the event we call the Big Bang wasn't a moment when our universe emerged from nothing. It was the moment when our brain universe collided with another brain universe floating in this multi-dimensional void. Imagine 2 massive parallel universes approaching each other after billions of years and finally touching. The tremendous kinetic energy this collision created instantly spread to every point of our brain, transforming it into an incredibly hot and dense energy soup. This is the Big Bang's starting moment. The explosion didn't emanate from a single point. It occurred simultaneously at every point of the brain, that is, our universe. This ekpyrotic model, from Greek meaning born from fire, offers elegant solutions to some of the Big Bang Theory's difficult questions. For example, it explains why the universe is so flat and uniform without needing inflation. The colliding brains being initially parallel and smooth ensures the resulting universe inherits these properties. More importantly, this model eliminates the singularity problem. The universe doesn't begin from a point of infinite density. The beginning is a physically definable event, an interdimensional collision. This, like the Big Bounce theory, also brings the possibility of a cyclic universe. Perhaps after colliding, the brains retreat, cool, and then approach each other again due to gravity's effect, triggering a new collision and a new Big Bang. This is an eternal cosmic dance governed not by time, but by interdimensional events. The origin of our existence might be the sound of a collision echoing in the depths of those hidden dimensions we cannot see. The entropy paradox. Why did everything begin so orderly? Whatever scenario we consider about the universe's beginning, whether a single explosion, an infinite bounce, or an interdimensional collision, all must face a much more fundamental and deep mystery. This mystery relates to time itself's nature and one of the universe's most fundamental laws, the second law of thermodynamics. This rule, known as the second law of thermodynamics, actually expresses a truth we all intuitively know. Everything in the universe moves from order to disorder over time. Ink dropped into a glass of water never collects at a single point on its own. Instead, it disperses and spreads throughout the water. A broken vase never repairs itself through its scattered pieces spontaneously coming together. This is because entropy, the measure of disorder in the universe, always tends to increase. This is time's one-way arrow, the invisible line separating past from future. The universe itself is subject to this law. Billions of years from now, stars will fade, galaxies will scatter, and the universe will reach an ultimate state of equilibrium and maximum disorder known as heat death, where everything is uniformly distributed and no work can be done. The universe's inevitable fate seems to be a one-way journey toward chaos. This is where that great paradox gnawing at our minds emerges. If the universe's ultimate goal and most probable state is absolute disorder, then why did it begin at its very start in the most orderly state possible? When we return to the Big Bang moment, the picture we encounter isn't chaotic confusion, but on the contrary, mind-boggling order and simplicity. The universe was in an incredibly hot, dense, and uniform state where every point had almost exactly the same temperature and density. This state might at first glance appear simple and chaotic, but from an entropy perspective, this is actually an extremely low entropy, extremely orderly beginning. All potential was evenly distributed throughout the universe. No complex structures had formed yet. Without this initial order, the universe's future wouldn't exist either. If the universe had begun with the most probable state, high-entropy chaos, matter could never have come together to form stars and galaxies. The planets where life could sprout couldn't have formed. The universe would have been dead the moment it was born. So the question is, why did the universe choose this impossibly special and orderly beginning that allows all this complexity to form in the future? Why does time's arrow point to future chaos while showing this perfect order in the past? When we add gravity's strange nature to this problem, the mystery deepens further. In most systems, increasing entropy means everything scatters. But in systems where gravity dominates, the situation is reversed. When a gas cloud collapses under gravity to form a star, it actually seems to achieve a more orderly structure. However, this process releases tremendous amounts of heat and radiation outward, which actually increases the universe's overall entropy, disorder. So all those magnificent structures we see, stars, galaxies, are just local, temporary byproducts of the universe's relentless march toward disorder. Their very existence is only possible thanks to that initial low entropy beginning. So what can explain this beginning? Some thinkers propose this is the past hypothesis, that the universe's beginning was simply a special state that must be accepted as a fundamental reality with no explanation. But this answer isn't satisfying for science's curious nature. While inflation theory explains why the universe is so uniform, it doesn't answer the question of why inflation itself began in such a special, low-entropy state. Perhaps the answer again lies in the multiverse idea. Perhaps countless universes are born in high-entropy, chaotic conditions and instantly vanish. We simply observe this situation because we live in the universe with that rare low-entropy beginning that allows us to exist. This suggests our existence results from winning a cosmic lottery. This entropy paradox isn't just a physics puzzle. It's a philosophical question reminding us how fragile and precious our existence is. We are children born from the universe's momentary order before chaos's inevitable victory. The Great Divide, when physics speaks two languages. On our journey into the universe's beginning, we've so far explored different and fascinating theories. But all these theories, however elegant, must navigate around a massive crack, a deep incompatibility lying at modern physics's heart. Our universe is like a book written in two different languages that can't agree with each other. One of these languages governs the magnificent dance of stars, planets, and galaxies, the world at large scales. This is the language of gravity, whose foundations Isaac Newton laid and Albert Einstein elevated to its peak with relativity theory. This language tells with flawless precision how the universe's fabric bends, how time slows, and how objects move on this cosmic stage. Thanks to this language, we can predict everything from a galaxy's movement billions of light years away to a satellite's position in our orbit. This is the physics of order, certainty, and large structures. But when we turn the page of the universe's book, we encounter a completely different, counterintuitive, and almost magical language. This is quantum mechanics language, governing the strange and probabilistic world of atoms and subatomic particles. In this language, particles can be in multiple places simultaneously, remain mysteriously connected no matter how far apart they are, and their existence is a cloud of probabilities until an observation is made, rather than definite reality. This is the physics of uncertainty, randomness, and invisible fields. Almost all our modern technology, from our cell phones to our computers and medical imaging devices, is built on our ability to understand and use this strange language's rules. Both theories, Einstein's general relativity and quantum mechanics, are the most successful scientific theories ever made in their own domains. Countless experiments and observations have repeatedly confirmed their predictions with mind-boggling precision. The problem begins exactly here. When these two magnificently successful theories come together, they become meaningless. They refuse to understand each other's languages. Gravity's large-scale, smooth world and quantum mechanics' small-scale, probabilistic, pixelated world cannot be mathematically unified. This often isn't a problem. When calculating a planet's orbit, we don't need to consider the quantum behavior of the atoms making up that planet. Similarly, when examining an electron's behavior, we can ignore its weak gravitational effect. But in the universe's history, there are places and times where these two languages must be spoken simultaneously. One is the singularity at a black hole's center, where massive mass is compressed into an incredibly small area. Gravity is extremely powerful, but the area it affects is quantum scale. The other, and more important for us, is the universe's beginning, the Big Bang moment. At that moment, the entire observable universe was compressed into a point smaller than an atom. Gravity was the universe's most dominant force, but the playing field was entirely quantum. To understand this moment, we need a new translator who will unify physics's two languages and make them speak in a common tongue. These two theories' inability to merge isn't just mathematical annoyance, it's the greatest obstacle to understanding the universe's most fundamental secrets. To truly understand what triggered the Big Bang, what happened before that first moment, how time and space themselves emerged, we need to reach a deeper, more fundamental theory encompassing these two theories. This unifying theory is known as quantum gravity theory and is considered modern physics's holy grail. Finding it won't just fill in that missing first page of the universe's book, but will also forever change our perception of reality's most fundamental nature. because these two languages' incompatibility whispers to us that what we know about the universe isn't yet the whole story, that behind the curtain lies a much deeper, unified reality. The quest for quantum gravity, two paths to unity. The deep chasm between general relativity and quantum mechanics, modern physics' two fundamental pillars, is the greatest obstacle to understanding the universe's birth moment. The need for a theory that will unify these two different languages in a single narrative and explain gravity's behavior in the quantum world has directed scientists on a great quest that's occupied them for decades. This quest is called quantum gravity, and it's an extremely abstract and challenging journey extending beyond physics' known boundaries. On this journey, two main paths stand out that are fundamentally different from each other. The first is string theory, which stands out with its elegance and comprehensiveness. The other is loop quantum gravity, which redefines space and time's nature. String theory, as we touched on in a previous section, abandons the idea that particles are point-like entities. Instead, it proposes that everything at the most fundamental level consists of tiny one-dimensional energy threads vibrating at different frequencies. The most attractive aspect of this approach is that it doesn't separate gravity from other forces. According to it, gravity, like other forces, is a consequence of a specific vibration mode of these fundamental strings. The graviton particle, assumed to carry gravity, is also, in this theory, just one of the different notes strings can produce, like an electron or photon. This way, the theory offers the potential to unify all of nature's forces in a single mathematical framework, promising to fulfill one of physics's greatest dreams. But for string theory to achieve this elegant unification, reality must have a much more complex structure than we perceive. For the theory to have a coherent mathematical structure, the universe must have far more than 3 spatial dimensions. Generally, it requires 10 or 11 dimensions. The existence of these extra dimensions offers a completely new perspective on how everything behaved in the universe's first moments. Perhaps during the Big Bang, these extra dimensions played a key role in space's expansion or in determining the universe's fundamental constants. String theory transforms the universe's beginning into an event so rich and multi-layered that our three-dimensional minds can't grasp it. The other major path in the quantum gravity quest is loop quantum gravity theory, which starts from a completely different philosophy. This theory, without proposing extra dimensions or new particles like string theory, focuses on the problem's origin, space and time's nature. In Einstein's relativity, space-time is accepted as a smooth, continuous, infinitely divisible fabric. Loop quantum gravity challenges this idea. According to it, if quantum mechanics rules are universal, then space itself must also be quantized, composed of smallest indivisible units. Just as a computer screen consists of pixels or fabric consists of threads, space consists of a network formed by connecting these fundamental units called loops, a quantum foam. This idea fundamentally changes our understanding of the universe's beginning. If space consists of smallest indivisible units, then compressing everything into a single point of infinite density becomes impossible. This means the singularity concept predicted by general relativity and where the laws of physics collapse actually doesn't exist. According to loop quantum gravity, when the universe collapses toward a singularity state, the structure of these smallest space units resists further compression. This resistance transforms the collapse into a bounce, naturally returning us to the big bounce idea we mentioned earlier, a cyclic model where our universe was born from a previous universe's collapse. According to this theory, even time isn't a continuous flow. It could be a sequence of successive moments arising from fundamental quantum interactions. Perhaps the Big Bang wasn't the beginning of time, but just a moment when the universe transitioned from one quantum state to another. Both theories are strong candidates for solving quantum gravity's mystery, but both remain unproven. Testing them requires incredible energies, far beyond our current technology. Nevertheless, these theories offer us a window into how strange and unexpected reality's deepest levels foundation could be. The emergence of space and time, beyond the fundamental. In our effort to understand the universe's beginning, we've always started with a fundamental assumption. Time and space are the most fundamental, unchangeable stage where events occur. They're like an absolute ground that comes before existence itself, always present. But the quantum gravity quest pushes us to question even this most fundamental belief. What if time and space aren't as fundamental as we think? What if they're emergent properties arising as a consequence of much more fundamental, abstract processes, like waves on a lake's surface emerging from deeper waters' movement? This is an extremely deep idea that upends all our mind's familiar reality perception. To better understand this thought, we can consider the concept of temperature. Temperature seems like a fundamental property of the world to us. We feel whether an object is hot or cold. But when we go deeper into the microscopic world, we see that temperature, as such, doesn't actually exist. Temperature is a collective result of millions of atoms and molecules' average kinetic energy, how fast they're vibrating. Asking a single atom, "What's your temperature?" is meaningless. Temperature isn't a property belonging to a single particle, but a phenomenon emerging from many particles' interactions. Some physicists believe space and time could be exactly like this. At the most fundamental level, in quantum reality's depths, perhaps concepts like position or moment don't exist at all. In the quantum world, particles don't always have a definite position. They exist in a cloud of probabilities until an observation is made. So what if space itself has such a nature? Perhaps at the smallest scales, the distinction between here and there becomes meaningless. Reality might consist not of objects existing in space, but of interconnected relationships, an information network. Space could be an illusion arising at large scales when this relationship network becomes sufficiently complex and stable, just as millions of water molecules come together to form a smooth lake surface. One theory based on this idea is causal set theory. According to this approach, space-time isn't a continuous fabric, but a collection of discrete fundamental events or points connected to each other through cause-effect relationships. Between these points, concepts like distance or time don't initially exist. Only the relationship "this event caused that event" exists. When these fundamental causality chains form a sufficiently crowded network, at large scales, the space-time geometry we perceive as smooth and continuous emerges. This means space isn't an empty container, but a structure built from the events themselves. Loop quantum gravity theory also reaches a similar conclusion through a different path. By proposing that space consists of indivisible smallest units called loops, it implies there's a fundamental limit below which distance cannot be subdivided. If space consists of fundamental units, it makes sense that time would too. Some physicists propose that time isn't a continuous flow, but a series of discrete moments, like frames of a film. Time isn't a river flowing independently, but a property emerging from changes in quantum states. There could be a fundamental tick of the quantum universe, and we might perceive these ticks coming one after another as time's flow. These ideas' greatest and most shocking consequence is completely changing our view of the Big Bang. If time and space themselves had to emerge from a more fundamental reality, then the Big Bang can't be the beginning of time and space. It could more likely be a moment when these concepts emerged, took shape, a phase transition. There could be a phase before the Big Bang when the universe existed in an undefined, non-geometric quantum state where time and space didn't exist in the sense we know them. In this case, the question what was before the Big Bang becomes as meaningless as asking what's north of the North Pole, because for the word before to be valid, time must exist. These theories force us to rethink existence's most fundamental building blocks. Perhaps at reality's deepest layer, there's no matter, energy, or space-time. Perhaps at the foundation of everything lies a quantum code consisting of pure information and relationships that we're only beginning to understand. The holographic principle: reality as a projection. So far on our journey, we've searched for the universe's beginning within time, space, and matter. But what if all these concepts we consider most fundamental are only surface reflections of a much deeper reality? What if this three-dimensional universe we inhabit, with all its depth, texture, and complexity, is perhaps just an illusion? This idea that seems like science fiction is one of the ideas modern theoretical physics treats most seriously: the holographic principle. According to this principle, everything we experience, space's three dimensions, might actually be a projection, a reflection of information encoded on a two-dimensional surface in the very distant edge of our universe. To understand this idea, let's think about the small, shiny security label on a credit card in our wallet. This is a simple hologram, a two-dimensional flat surface. But when light falls on it, a three-dimensional image springs from within. The image has depth. It changes when you look from different angles. But all this three-dimensional information is actually stored on that flat two-dimensional film. The holographic principle takes this simple analogy and applies it to the entire cosmos. Our universe could be this massive three-dimensional hologram, and all the information composing it could be written on a massive two-dimensional screen at the universe's boundary. This mind-boggling idea arose from efforts to resolve a paradox concerning the universe's most mysterious objects, black holes. In the 1970s, physicist Stephen Hawking discovered that black holes aren't completely black. They slowly evaporate over time by leaking energy called Hawking radiation. This was a shocking discovery because it brought with it a major problem: the information paradox. According to classical physics, everything that falls into a black hole, all the information of a star or an astronaut, is forever erased from the universe when the black hole evaporates. But one of quantum mechanics' most fundamental rules says information can never be destroyed, it can only change form. This was an apparently irresolvable contradiction between physics's two fundamental pillars. Information both vanishes inside a black hole and cannot. A solution to this paradox came in the 1990s from physicists like Gerard 't Hooft and Leonard Susskind. They proposed that information falling into a black hole doesn't actually disappear. Instead of falling into the black hole's interior, the information could be stored, encoded like a kind of hologram on the black hole's two-dimensional surface, its event horizon. As an object passes through the event horizon, all its three-dimensional information, mass, spin, structure, was written on this surface. Thus, when the black hole evaporates, this information also returns to the universe with the radiation. This was a radical idea. Everything inside a three-dimensional volume could be completely described by the two-dimensional surface surrounding it. This is where that great intellectual leap occurred. If this principle applies to a black hole, a region of space-time, why shouldn't it also apply to the entire universe? Perhaps our three-dimensional universe is a reflection of information encoded on a massive cosmic horizon surrounding it. This means everything we experience, the solar system, the Milky Way galaxy, and even the atoms making up our bodies, is actually a consequence of a much more fundamental two-dimensional information field. Space and time aren't the universe's fundamental stage, they're properties emerging from this deeper information layer. just as a three-dimensional game character on a computer screen is actually born from two-dimensional code behind the screen. If this principle is true, our understanding of the Big Bang also completely changes. It's no longer a chaotic explosion starting from the point. Perhaps it was a kind of phase transition, the moment when this two-dimensional information field began projecting our three-dimensional hologram. The universe's birth wasn't the creation of matter and energy from nothing. It was the organization of information itself to form the reality we perceive. This means the universe's most fundamental fabric might not be matter or energy, but pure information, and we might be nothing more than a three-dimensional expression of this information. Reality itself might be a two-dimensional poem written in a cosmic alphabet we're just learning to read. It from bit, the universe as computation. If the idea that our three-dimensional reality could be just a reflection of a two-dimensional information surface lights a bulb in our minds, then the next logical step, illuminated by this light, leads us to an even more surprising landscape. If information lies at the universe's foundation, this information must somehow be processed, organized, and transitioned from one state to another. This thought places information theory, originally developed to study communication systems, at cosmology's heart, and offers us a completely new lens through which to view the universe. Perhaps our universe is less a collection of physical objects and more like a massive computer, constantly calculating its own state. At the center of this approach lies the idea that everything in the universe, at its most fundamental level, can be described with units of information called bits. A bit is information's smallest and most fundamental unit, representing a choice between two possibilities, like a flipped coin coming up heads or tails. According to this theory, an atom's position, a star's temperature, or a galaxy's rotation speed might ultimately be nothing more than an incredibly complex combination of these fundamental yes or no choices, bits. If this is true, then matter, energy, space, and time aren't reality itself, but results arising from how these fundamental information bits are arranged and processed. The universe is the hardware itself, and the laws of physics are the software running this hardware. From this lens, the Big Bang stops being just a physical explosion. It could more likely be the moment when this cosmic computer's power button was pressed, when the program started running. Perhaps before the Big Bang, information existed in a completely different, simpler form. Perhaps it was that first quantum code that would form our universe. With the Big Bang, this information began being processed, evolving, and creating the complex structures we see today. This could also bring an elegant explanation to the entropy paradox. The universe's initial incredibly orderly, low-entropy state might have resembled that first, simple, clean state when a computer program starts. As the program runs and calculations are made, information content increases, and the system's complexity, entropy, naturally rises. This idea also fundamentally changes our perception of time's nature. If the universe is fundamentally a computation, then time might not be a smooth, continuously flowing river as we experience it. Instead, like a computer processing data in successive discrete steps, time might also be a series of discrete moments. The universe transitions from one state to the next, from one computational step to another. This might help us understand some of quantum mechanics' strangest features. Events like particles seeming to jump from one place to another without passing through the space between might simply be the system's transition from one state to the next calculated state. So what does this cosmic computer run on? The black hole information paradox and holographic principle might offer us a clue. Perhaps this massive computation is processed into space itself's fabric, that fundamental quantum foam. Space itself could be a giant quantum computer. In this view, every unit of space has a certain information storage capacity, and the universe's evolution is nothing more than processing this information according to quantum laws. Quantum entanglement, two particles remaining instantly connected no matter the distance between them, could be evidence of how deeply and strangely connected this cosmic computer's processors are. Perhaps space-time itself is a structure arising from this entanglement network. Of course, this brings us to an ultimate question. If the universe is a computer and the laws of physics are its program, who or what wrote this program? What runs this cosmic computation? These questions extend beyond science's boundaries into philosophy's realm. But despite these ideas' speculative nature, the intersection of information theory and cosmology is becoming an increasingly active research area. While trying to solve our most complex problems like quantum gravity, scientists are increasingly turning to information-based principles. Because perhaps the universe's secret isn't hidden in the smallest particle or the largest galaxy, but in those invisible information bits defining the relationship between the two. Emergent gravity. Is the force an illusion? The idea that the universe's fabric at its most fundamental level might consist of information, and that this information is processed like a giant cosmic computer, directs us toward radical questioning about nature's most familiar yet most mysterious force, gravity. From Newton to Einstein, we've always thought of gravity as the universe's fundamental, unchangeable feature, a fundamental force existing in matter's nature and bending space-time's fabric. But what if gravity isn't a fundamental force as we think? What if it too, like temperature, is a statistical consequence of deeper, more fundamental phenomena, a byproduct? This is the revolutionary idea known as emergent gravity, which removes gravity from being one of the universe's fundamental pillars and redefines it as a result, an illusion. One of this approach's best-known advocates, physicist Eric Verlinde, proposes that gravity isn't a fundamental force, but an entropic force. This means gravity arises from the universe's fundamental tendency to maximize disorder, from entropy. To understand this idea, let's consider air molecules in a room. These molecules tend to spread throughout the available space rather than gathering in just one corner of the room. This is a natural consequence of entropy. The system seeks the most probable, most disordered state. According to Verlinde, gravity also arises from a similar principle. Matter disturbs the information structure in space-time. The universe moves matter toward each other to minimize this information disturbance and maximize entropy. What we perceive as gravity is actually a consequence of the universe's effort to optimize information order. This means gravity behaves not like a pulling force, but more like a pushing force. However, this push is created not by other objects, but by the system's own statistical behaviors. This is in perfect harmony with the holographic principle, too. If all the universe's information is encoded on a two-dimensional surface, then gravity in our three-dimensional world could be arising from this two-dimensional information's thermodynamic properties, heat and entropy laws, just as temperature emerges from atoms' movement. One of this theory's most striking and controversial consequences is the potential explanation it brings to the dark matter mystery. For decades, astronomers have thought a mysterious type of matter we can't see, but whose gravitational effects we feel, must exist to explain galaxies' rotation speeds. According to our observations, galaxies' outer regions rotate too fast to be explained by just the gravity created by visible stars and gas. We call whatever provides this extra gravitational pull dark matter. But despite years of searching, we haven't found any direct evidence of what this mysterious matter is. Emergent gravity theory offers a completely different possibility. What if there's no missing matter? What if what we've misunderstood is gravity itself? According to Verlinde's models, at very large scales, like intergalactic distances, gravity begins behaving slightly differently than Einstein predicted. This stems from this entropic root in gravity's nature. This small deviation creates exactly that extra gravitational effect needed to explain galaxies' rotation. So what holds galaxies together isn't an invisible matter halo, but a property of gravity itself, emerging at large scales that we don't yet fully understand. This doesn't completely reject dark matter's existence, but suggests we need to rethink its role. Perhaps the reason we can't find this mysterious component of the universe is that we're looking in the wrong place. Perhaps the answer lies not in a new particle, but in a gap in our understanding of the nature of the force we considered most fundamental. Emergent gravity is still a highly speculative theory, far from being proven, but it shows us how deceptive reality can be. Even the laws we consider most fundamental might perhaps be nothing but shadows behind a deeper curtain. If gravity isn't a fundamental force, this requires us to completely redraw our entire picture of the universe's beginning, because the laws shaping the universe in those first moments could be completely different from what we experience today. Even gravity might have appeared, only after some point in the universe's evolution. Primordial black holes, the universe's ancient ghosts. Beyond all those grand theories about the universe's beginning, a silent and invisible possibility lies hidden in creation's first moment's unimaginable chaos. This possibility is neither a new force nor an unknown particle. It's the cosmos's oldest ghosts, born from the universe's very first fire, primordial black holes. These dark objects are completely different from the black holes we know formed by the collapse of massive stars at life's end. They weren't born from stars' ashes, but from the universe's own dough, from those first moments' extremely dense conditions. They are the Big Bang's forgotten children. Let's visualize that moment in our minds. In the first seconds after the Big Bang, the universe consisted of an incredibly hot and dense soup of energy and particles. In this primordial plasma, everything was in constant flux. But this flux didn't have perfect uniformity. As a legacy of quantum fluctuations, some regions were momentarily much denser than others. In most places in the universe, these density differences softened and dispersed as the universe expanded, transforming into those gentle fluctuations that would later form galaxies' seeds. But what if in some regions the density exceeded a critical threshold? What if a region became so extremely dense that even the universe's expansion's pushing force wasn't enough to disperse it? That's when gravity enters the stage. In that momentarily extremely concentrated region, gravity's crushing force would triumph over all other forces. That region would instantly collapse under its own weight. This wasn't a slow and magnificent process like a star's death lasting millions of years. It was faster than an eye blink, instant and violent birth. While the universe itself was still in infancy, it had created the first black holes from its own fabric. These are what we call primordial black holes. Their existence means they've been with us since the very beginning of the universe. They're not structures formed later. They could be some of the cosmos's fundamental building blocks. One of primordial black holes' most fascinating features is that their sizes could show incredible variety. Stellar black holes are limited by the collapsing star's mass and generally must be at least several times the sun's mass. But there's no such lower limit for primordial black holes. They could have formed in any size, depending on that first moment's density fluctuation's magnitude. Some could be microscopic black holes, smaller than an atom. Some could fit in our palm while having a mountain's mass. and some could be massive monsters, tens of thousands of times larger than the Sun. The universe might have created a mysterious population of black holes in every conceivable size in the first moment of its existence. So what happened to these ghosts? According to Stephen Hawking's revolutionary theory, black holes aren't completely eternal. Over time, they evaporate very slowly through a process called Hawking radiation, leaking energy. This evaporation rate is inversely proportional to the black hole's mass, meaning small black holes evaporate much faster. In this case, the smallest microscopic black holes formed in that first moment have long since evaporated throughout the universe's history, quietly exiting existence's stage. But larger ones, primordial black holes with an asteroid's mass or more, have an evaporation time much longer than the universe's 13.8 billion-year age. This means if they formed, these larger primordial black holes are still among us. They're invisible, ancient hunters, quietly floating in our galaxy's dark voids between stars. Their existence can only be detected by their gravitational effects, by how they bend light around them, or by the effect they create if they happen to approach a star. This idea leads us to an exciting possibility. What if the answer to one of the universe's greatest secrets lies hidden in these invisible ghosts? A large part of the universe is missing. Astronomers have been facing this disturbing truth for decades. When we examine the universe's large-scale structure, from galaxies' rotation speeds to how galaxy clusters hold together, the matter we see, stars, planets, gas, and dust clouds, makes up only a small portion of the gravity needed to hold these structures together. According to our calculations, about 27% of the universe's total mass energy density must consist of completely invisible, mysterious matter that doesn't interact with light in any way. We call this unknown substance dark matter. We don't know what it is, we only know it exists, that it shapes the universe's fabric through gravity. The most popular theory to solve this cosmic mystery is that dark matter consists of a new subatomic particle we haven't yet discovered, particles given names like WIMPs or axions. These hypothetical particles could form a ghost sea passing through everywhere in the universe, even through us, unnoticed. For decades, scientists have tried to catch one of these particles using the world's most sensitive detectors in laboratories set up deep underground. But despite all these efforts, the result has always been the same: silence. We still have no concrete, direct evidence about dark matter's nature. This situation has pushed some scientists to more seriously consider alternative possibilities. What if what we're looking for isn't an exotic new particle? What if the answer has been with us since the very beginning, from the universe's first moments? This is where the universe's ancient ghosts, primordial black holes, re-enter the stage. If these black holes formed in sufficiently abundant quantities in those first chaotic moments after the Big Bang, they could constitute all or at least a significant portion of that missing mass in the universe today. This is an extremely elegant idea because it doesn't require a new, unproven physics theory. Primordial black holes' formation is entirely possible within the framework of physics laws we know, general relativity, and the standard cosmological model. They naturally do everything dark matter is supposed to do. They're completely electromagnetically dark. They don't emit, reflect, or absorb light. But they have mass and therefore interact with matter through gravity. Just as dark matter is supposed to, they could form an invisible halo around galaxies, making them rotate faster. If dark matter is actually a population of billions of primordial black holes of different sizes scattered throughout our galaxy, why haven't we found them yet? The answer lies in their nature. These black holes are individually extremely small and very far apart from each other. Seeing them directly is impossible. The only way to detect their existence is through gravitational effects. For example, through an effect called gravitational lensing. If a primordial black hole happens to pass between us and a distant star, its gravity will bend the star's light momentarily like a lens, focusing it. This is observed as a brief, sudden increase in the star's brightness. Astronomers have been searching for such microlensing events for years and have detected some. But the number found so far isn't sufficient to explain dark matter entirely with primordial black holes. But this doesn't mean it's the end of the story. Perhaps these black holes are concentrated in a certain mass range, making them harder to detect. Or perhaps dark matter isn't a single thing, but has a mixed structure consisting of both primordial black holes and undiscovered particles. Additionally, these ancient objects could solve another great cosmic mystery, the origin of supermassive black holes. Today, nearly every large galaxy's center contains massive black holes, with masses millions or even billions of times the Sun's. How these monsters grew so large when the universe's history is so young is one of astronomy's greatest puzzles. Primordial black holes could be these giant seeds. If slightly larger than normal primordial black holes formed in that first moment, they could have rapidly swallowed surrounding gas and dust, transforming into today's supermassive black holes in the universe's early periods. As the dark matter search continues, the primordial black holes idea offers us a different perspective. Perhaps the answer to one of the universe's greatest mysteries isn't hidden in a new exotic particle. Perhaps the answer lies in the most extreme manifestations of the oldest and most familiar force, gravity. The invisible architects of the universe could have been shaping the cosmos we observe since time immemorial. The cosmic microwave background, the universe's baby photo. Our journey now leads us to the universe's oldest monument, an echo remaining from time itself. This is a ghost shimmer filling every corner of the sky, whose source we can't see even with our most powerful telescopes. Scientists call it the cosmic microwave background radiation, but we can give it a more poetic name, the universe's baby photo. This is a faded picture taken nearly 14 billion years ago when the universe was still a baby, engraved into time's fabric. This picture is a priceless archive containing answers to our most fundamental questions about existence. To understand how this light formed, we need to go to time's beginning, to the universe's first 380,000 years. In that period, the universe was a very different place from what we know today. Not cold and dark, but on the contrary, incredibly hot, dense, glowing like a mist cloud. This was a boiling plasma sea consisting of free electrons, protons, and photons, light particles. In this environment, light couldn't travel freely. The moment a photon tried to travel even a tiny distance, it would collide with a free electron and immediately change direction. This situation had trapped light inside the universe. That first universe was brighter than even the sun's center, but at the same time completely opaque. If you were standing in it, you'd see nothing but blinding, dense fog blocking your view. Then, as the universe expanded and cooled, one of history's most important moments occurred. The temperature dropped low enough to allow atoms to form. Free electrons were captured by protons, forming the first stable hydrogen and helium atoms. We call this event recombination, reunification. This moment was a turning point for the universe. Those free electrons constantly blocking light's path had now disappeared. Suddenly, the path opened for photons imprisoned for billions of years. Light that had constantly been colliding and bouncing until that moment was suddenly freed and began an unobstructed journey in every direction of the universe. The universe became transparent for the first time. That first light released at that moment, that cosmic dawn, is the light we detect today as the cosmic microwave background radiation. Of course, this light has undergone change during its 14 billion year journey. As the universe expanded, this light's wavelength also stretched. Initially, in the visible light and ultraviolet range, this glow cooled over time, losing energy, and stretched to the very cold microwave range we can only detect with radio telescopes today. But in essence, it's still the same light, an echo of that first moment of creation, evidence of the moment the universe first inhaled and exhaled. When we look at this baby photo, the first thing we notice is that it has almost perfect uniformity. No matter which direction we look in the sky, this radiation's temperature is almost exactly the same. This situation constitutes one of inflation theory's strongest pieces of evidence. But this picture's real secret lies not in this uniformity, but in its tiny flaws. If we examine this radiation much more precisely, we see there are tiny fluctuations on the order of 100,000th in this uniform temperature. These tiny hot and cold spots, shown in different colors on maps, aren't the picture's noise or errors, they're the picture's most important parts. These tiny temperature differences are a direct reflection of density differences in the universe's first moments. The slightly warmer blue spots represent regions where matter happened to be slightly denser. The slightly cooler red spots are places where density was slightly less. These faint differences were the seeds of the universe's entire future structure. Over billions of years, gravity slowly gathered matter in these slightly denser regions. These seeds sprouted, first creating the first stars, then galaxies, and finally the massive galaxy clusters and cosmic web we see today. Every galaxy we look at owes its existence to one of those tiny color tone differences in this ancient photo. That's why this radiation isn't just a picture, but also a prophecy, a cosmic map where the universe's future is written. But in this map, there are also some anomalies, mysterious and unexplained things that don't quite fit our current understanding. The perfect picture the universe presents us is one of standard cosmology's model's greatest triumphs. Those tiny temperature fluctuations are an almost flawless agreement with what our theories predict. But when we look more closely, we notice some strange, unexplained traces on this smooth surface. These are cosmic anomalies that don't quite fit our current understanding, whispering that we don't yet know the whole story. These anomalies are cracks in our standard model, and perhaps through these cracks, light from a completely new physics is leaking. The most famous of these mysteries is the region known as the cold spot. In an area in the CMB baby photo's southern hemisphere, there's an unusually large and cold patch. Discovered by the WMAP satellite and later confirmed at higher resolution by the Planck satellite, this spot is much more pronounced than statistically expected. Of course, the simplest explanation is that this is just a statistical coincidence. In a map consisting of millions of random points, some regions can be expected to be coincidentally colder or hotter. This could be a rare but not impossible situation expected to appear in the universe's massive data set. But for many scientists, this answer isn't satisfying, and they're investigating deeper possibilities. One idea is that behind the cold spot lies a massive structure hiding between it and us, a supervoid. This is an ocean of nothingness billions of light years wide, containing far fewer galaxies and matter than normal. According to theory, as light traveling from the universe's first moments passes through this massive void, it loses some of its energy. This energy loss causes us to perceive light from that region as colder. Astronomers did find a supervoid in that direction, but there's a problem. The void found doesn't appear large or empty enough to alone explain the cold spot's extreme coldness. This situation opens the door to a much more exotic whisper. What if the cold spot is a trace of a collision our universe experienced in the past with another bubble universe in the multiverse ocean? According to this scenario, this contact with another universe could have drawn energy from that region of our universe, leaving a permanent cold trace. If this is true, it could be the first concrete evidence of other universes' existence. The cold spot is a kind of cosmic bruise, a faint memory of interdimensional contact. Another confusing anomaly is what's dramatically called the axis of evil. This name, of course, doesn't carry a malevolent meaning. It describes a surprising alignment that challenges one of the universe's most fundamental assumptions, the cosmological principle. According to this principle, the universe should be the same in all directions on large scales, meaning there should be no statistical difference between looking in one direction versus another. But the largest scale temperature fluctuations in the cosmic microwave background seem to violate this principle. Instead of being randomly distributed, these fluctuations tend to align along a certain axis in the sky. Could this be an illusion? Perhaps this alignment results from our position within the Milky Way galaxy, or from a systematic error in our measurement methods we haven't yet noticed. Scientists have made great efforts to eliminate these possibilities, but this strange alignment persists. So, if it's not an error, what does it mean? This would mean the universe has a preferred direction at the largest scales. It would mean the universe could have a direction inherently built into its fabric. Perhaps during inflation, space-time's expansion wasn't completely equal in all directions. Perhaps our universe carries an effect from the larger structure it fills. These anomalies might appear as small blemishes on the universe's baby photo, but they could be harbingers of great discoveries. These traces could be road signs leading us beyond the physics we know to a completely new reality. Polarization patterns, hidden signatures in the universe's first picture, are only the surface layer of the story. Now it's time to go deeper, to read a much more hidden, much subtler signature engraved into light itself. Beyond temperature fluctuations, this ancient light has another property we call polarization, light waves' tendency to vibrate in a certain direction. Like sunlight reflected on a calm lake's surface being polarized at a certain angle, the universe's first light was also polarized and sorted in certain ways by events in those first moments. These patterns carry even more information than the temperature map. They're the universe's birth moment's hidden handwriting. The part of this polarization known as E mode is the expected, more easily found pattern. These patterns naturally arise from density differences in the universe's first moments, like a stone thrown into a puddle creating circular waves. Those first density differences in matter also created these predictable polarization patterns in light. E-mode's detection confirmed our standard cosmological model's predictions and further refined our knowledge about the universe's structure in that period. They're reliable witnesses confirming the part of the story we know. But the real treasure is hidden in an extremely difficult-to-detect pattern faint as a whisper called B mode, scientists' holy grail. Unlike E mode's circular, symmetric patterns, B modes have swirling, rotating patterns. There are two main ways these special patterns can emerge. One is gravitational lensing. During its 14 billion-year journey, as light passes by massive galaxy clusters, these clusters' gravity slightly bends light's path. This bending creates a slight swirling effect in light's polarization, secondary B modes. Examining even this signal is an invaluable tool for mapping dark matter's distribution in the universe. But the B-mode signal scientists are truly pursuing comes not from an effect occurring during this journey, but from an echo coming from creation itself, primordial gravitational waves. If cosmic inflation theory is true, the universe's mind-boggling expansion in that first moment must have created massive fluctuations in space-time fabric itself, a kind of space-time earthquake. These primordial gravitational waves must have left that unique, swirling B-mode signature on the universe's first light. Finding this signature won't just prove inflation, it will also give us direct information about how powerful that first expansion was. It's like hearing the universe's birth moment's sound. This hunt is extremely difficult. The signal is so weak that light emitted from our own galaxy's dust can easily mimic it and mislead us. Past exciting announcements about finding this signal later turned out to be illusions from this cosmic dust. But this difficulty doesn't discourage scientists. From telescopes at the South Pole to new generation satellites planned to be sent to space, like Lightbird, experiments around the world are becoming increasingly sensitive to separate this ghost signal from cosmic noise. Deciphering these patterns means not just proving inflation, it means understanding space-time's nature, revealing fundamental laws in the universe's first moments. This has the potential to find first clues about how gravity unites with the quantum world. The cosmic microwave background radiation is an ancient text that continues whispering new secrets to us as long as we look. And its deepest secrets might be hidden in its finest, hardest-to-read lines, those vague polarization patterns. The quest will continue until we hear the universe's first whisper. The simulation hypothesis. Are we living in code? Our journey into the universe's beginning has brought us to time and space's most distant boundaries, that fine line where science and philosophy intersect. Now it's time to stand on this line and ask perhaps the most shocking question of all. What if all this reality, everything we know, touch, feel, isn't fundamental reality? What if our universe is nothing more than a massive simulation designed by incredibly advanced intelligence? This possibility, that initially seems like science fiction, is seriously considered by many thinkers and scientists. According to the idea known as the simulation hypothesis, our universe, with its own laws of physics, history, and even conscious beings, could be a computer program running inside a much larger reality. At the heart of this thought lies a simple but impossible to answer question. How do we know the universe we observe is real? After all, our reality experience is shaped by our senses, and we know very well our senses can be deceived. If a civilization was millions of years ahead of ours, couldn't it possess technology to create a virtual universe so complex and perfect it's indistinguishable from reality? This question causes us to question our most fundamental assumptions about existence. If we're living inside such a simulation, could there be a way for us to notice? Perhaps yes. Perhaps in this simulation's fabric lie faint clues, a kind of error or flaw suggesting its artificiality. The first of these clues could be hidden in the universe's nature at the smallest scales. Quantum mechanics whispers to us that space and time might not be a smooth, continuous fabric. At the most fundamental level, reality might have a pixelated structure. Just as a digital photograph consists of millions of individual pixels when viewed closely, space might consist of indivisible smallest units. If these cosmic pixels' existence is proven someday, this could be a strong sign that our universe runs on an information processing system. It would mean reality's foundation consists not of continuous but discrete information pieces, just as computer code consists of zeros and ones. Another potential clue is hidden in those fundamental constants governing our universe: gravity's strength, light's speed, and electrons' mass. These numbers appear incredibly precisely tuned to allow life to exist. If any of these numbers were slightly different, stars would never form, planets couldn't stay in orbit, and life as we know it would be impossible. Is this fine-tuning coincidence or a sign of design? If we're living inside a simulation, these constants could be parameters carefully chosen by programmers to ensure the universe runs stably, just as an engineer sets a virtual world's rules. Of course, this is a highly speculative idea, far from being proven, and many scientists approach it with skepticism. There's also a philosophical counterargument. Even if our universe is a simulation, does this make it less real? For us, our experiences, thoughts, and emotions are real. The fact this reality was produced by a computer program doesn't change its meaning for us. In this sense, the simulation hypothesis is a thought experiment that forces us to rethink our understanding of existence rather than refuting reality. But this idea's cosmological consequences are profound. If the universe is a simulation, what does the Big Bang mean? Perhaps it was the moment the simulation was initiated, when the program was run. This might explain some mysteries like why the universe began in such an orderly state. Perhaps the biggest question is, if there's a program, who are the programmers? This leads us to the idea there could be superior beings, perhaps far beyond our own intelligence, possibly communicating with us, observing us. Whatever the answer, the simulation hypothesis takes our curiosity about the universe to extreme limits. Perhaps someday we'll be looking for a trace this simulation left in cosmic microwave background data, like a glitch in a computer game. Time's arrow and causality, illusions of order. One of the most fundamental intuitions rooted in our minds is time's relentless flow. We experience it as an invisible river connecting past to future, always flowing in one direction. Another fundamental pillar standing on this river's shore is causality, the principle that every result has a cause, and the cause always comes before the result. These two concepts form our reality perception's foundation, their unquestioned rules enabling us to make sense of the world. But as we approach that first moment when the universe was born, that moment of mind-boggling density and energy, even these most reliable guides might abandon us. In those first moments, time and causality might not be valid in the sense we know them. According to the classical view, time began with the Big Bang. That moment was both the universe's and time's birth moment, the causality chain's first link. But this simple picture becomes complex when confronted with quantum mechanics' strange world. At the smallest scales, reality's fabric is radically different from our everyday experiences. Particles can live multiple fates simultaneously. Events proceed through probabilities rather than definite outcomes, and causality's rigid, unshakable rules might not be so clear in this foggy, uncertain world. If the universe was born from this quantum uncertainty, shouldn't it have been subject to these strange rules in its infancy? This question leads us to one of the deep theories about time's nature, the block universe model. According to this theory, time's flow is just an illusion. Past, present, and future all exist simultaneously. The universe's entire history is like a book written from beginning to end, or a film already shot. We just turn the pages one by one, or watch the film's frames in sequence, but the whole story is already there. According to this view, the cause-effect relationship is nothing but a concept created by our limited perception. Everything already stands frozen within a four-dimensional space-time block that exists. Another possibility is that time isn't an illusion, but initially had a much more chaotic and non-linear structure. Let's think about a black hole's event horizon. There, under gravity's extreme power, we know time and space don't behave as we know them. They bend and deform. If time can behave so strangely at a black hole's edge, how might it have behaved in those first moments when the entire universe was denser than even a black hole? Perhaps time didn't begin flowing like a smooth, continuous river. Perhaps it had a chaotic beginning, full of tiny, unpredictable jumps or pauses caused by quantum fluctuations. In this chaotic beginning, the causality chain might also have broken. Perhaps at some moments, results came before causes, or there was never a clear connection we could understand between them. This is an idea completely contrary to our logic, but the universe's first moments didn't have to obey our logic's rules. It was a quantum foam where everything was possible, where a completely new book's first words were being tried. Where can we find evidence of these deep and abstract ideas? The answer again might lie hidden in the universe's baby photo, the cosmic microwave background radiation. Some strange anomalies or unexpected alignments we see in that radiation's patterns might be ghost traces of the universe's first chaotic moments, a period when causality hadn't yet fully settled. Those patterns might be telling a more complex story than classical physics's simple beginning predicts. Perhaps time's arrow is an emergent property, naturally arising as the universe expands and cools and entropy begins increasing, not a fundamental rule existing from the very beginning, but a consequence of the universe's evolution. This whispers that even our existence's most fundamental pillars aren't absolute, that they too once didn't exist and might lose their meaning again in the universe's distant future someday. Epilogue: Finding Peace in Mystery. We began tonight's journey from nothingness's deepest point. We imagined quantum foam's whispers, those first sparks giving birth to universes. We stretched beyond time and space, swimming in the multiverse's infinite sea of possibilities. We considered that reality's fabric might be woven from strings, or perhaps pure information. We whispered that gravity might not be a fundamental force, but an illusion. We questioned whether the universe's oldest ghosts, primordial black holes, are the cosmos's architects. And finally, we wandered at the boundaries of the idea that our very existence might be a giant simulation, and time perhaps just an illusion. And now, as this cosmic journey ends, allow your mind to slow. Our aim wasn't to find definitive answers to all these questions. The aim was to find beauty, serenity in those answers' absence, in that great mystery itself. Just as we look at the night sky and find peace before that vista's majesty, even without knowing each star's name. Now close your eyes and imagine those bright galaxies in your mind, those dense thought clusters slowly moving away from you. They're no longer problems to be solved. They're now just distant, sparkling points of light. Trillions of galaxies slowly dimming in your mind's depths. Each one a thought the day brought, a memory, a worry, and all of them now finding their place in the universe's infinite expanse, moving away from you. Begin to feel your body's weight. Gravity, this mysterious force we talked about all night, is now gently and compassionately pulling you toward your bed. Don't resist this feeling. Let that secure pull embrace you. With each inhale, feel fresh tranquility filling your body, and with each exhale, allow the day's last remnants to drift away into this cosmic void too. Feel your shoulders relaxing, your arms and legs growing heavy, your mind transitioning from that active state to a calm, potential-filled state, like in the universe's first moments. Now there's only silence, like that deep, velvety void between stars. This silence isn't frightening. On the contrary, it's restful. This is like that quantum vacuum we talked about. From outside, it may appear calm, but within it harbors infinite potential for dreams to be born, for the body to repair itself. The last thoughts in your mind are like those virtual particles appearing and vanishing momentarily. You no longer need to hold on to them. Let them exist and then dissolve into nothingness. Our journey ends here. You're gently drifting from curiosity's bright shores toward sleep's peaceful, deep ocean. The answers will still be there tomorrow, but now just rest. Good night.